Right, I'm going to talk about PIDs, PIDs as they're sometimes called, and PID stands for something. Obviously the P stands for proportional, the I stands for integral, and the D stands for derivative. So there's everything you need to know about PIDs. No, it's not, of course, I'm joking. It's actually quite a complex thing, but I'm going to try and distill it down now. I'm taking a few liberties to make life a little easier for all of us, and I'm going to give these other names. I'm going to give these, and you'll see why in a moment. I'm going to give proportional, I'll give it the name present, as in right now. Integral, I'm going to give it the name past, as in it's already happened. And derivative, I'm going to give it the name future, as in hasn't happened yet, but it's going to. These are the alternative definitions. Well, this is how things work, and I'm going to explain how that works. Now, let's assume this is a mini quad. There it is. Beautiful, isn't it? Gorgeous. I've taken the propellers off because it's always safer to work on the whiteboard without propellers on. And this mini quad has the ability to tilt and whatever, and so we have inputs which go into it from our flight controller. This is all on, here's our flight controller, it's got all this stuff on it here. All this is in our flight controller. This is the magic that makes things happen. And also in the flight controller there is another block which is the sensor, which actually, we'll just put it over there. And the sensor provides the information that goes off to the derivative, the integral, and the proportional. So I can draw some lines around these to show you what I am talking about. These are actually separate bits of stuff. They're actually software inside the flight controller that handle these particular operations. So what we have here is a feedback loop. This is a feedback loop. Basically, here's our quad. If our quad tilts, this little bit here, the gyro or the accelerometer, picks up the fact it's tilted, feeds the information into these things here, the PID software, which then has some outputs. There's a proportional output, an integral output, and a derivative output. They're all mixed up here and then fed back into the quad to correct it. So it's a feedback mechanism that works a little bit like this. Say you're running yourself a nice hot bath and you turn on the taps. Woohoo, all good. Put your hand in. Whoa, it's too hot. What do? You turn down the hot tap. That's the feedback. So first of all, you sense, oh, it's too hot. That's the sense, that's the spit. And then you say, you work out what to do. If it's too hot, I need to turn down the hot tap. So come out here, and then you put that in, and the response is that you turn down the hot tap. Then it gets too cold. Oh, I need more hot water. So you turn the hot tap back up. So you're constantly monitoring through your sensor and feeding back through this feedback loop to make sure that the temperature is stable and at the temperature you want. That's really simple when it comes to things like running a bath. But when it comes to flight controllers, it gets a bit more difficult because lots of things are happening very quickly. So let's discuss what proportional is. Proportional is like saying, oh, it's too hot, add cold water. Or it's too hot, turn down the hot water. And the amount, if it's really, really hot, then you might turn the hot water right off and let the cold water cool it down. So the amount of adjustment you make is proportional to the amount that the correction needs to be. So let's say you're flying your quad. I've got a uni-quad here. Let's say you're flying, wrong color, it doesn't contrast well on the board, does it? Let's say you're flying your FPV glasses and it tilts like that. Now, if it tilts a little bit, well, you only need a little bit of correction through the feedback to bring it back to level. If it tilts a lot, you need a whole lot more correction. So the amount of correction is proportional to the amount that it's veered away from the desired attitude. So the more the quad tilts or banks, then the more feedback you'll get through this proportional thing. And it's right now. If the quad is at 45 degrees right now, then the feedback will be 45 degrees worth of feedback. If it's at 90 degrees right now, it'll be 90 degrees worth of feedback. So that controls the amount of change in the motor speeds and everything. That's really simple. And you might think, whoa, that is so simple. And another way I like to do it, or to mention it, or talk about it, is, let me get rid of these pens for a start. Here's, see if I can get it, here you go, see? This is my stopwatch. Now, obviously, as I move this away from its, if I let it go, it just hangs there, right? It just hangs vertically down because gravity is pulling it down. If I move it away from that perpendicular position, or the vertical position, then gravity tries to pull it back. And the further I pull it out, the more the force of gravity is having an effect. So if I move it out a little bit, then it's only really moving a bit. Up there, I can feel a lot of force trying to pull that back to the vertical position. So the effect of gravity is proportional to the angle at which I move this. And you might think, well, hey, that's really cool, because all you've got to do is just have this proportional thing. If the bath's too cold, add hot water. If it's too hot, add cold water. Simple. What could go wrong? Well, I'll show you what could go wrong. If I take this and let it go, whoa, hang on, it's swinging. It doesn't just go back to the vertical and stop. it's going past it. It's overshooting because proportional on its own doesn't work very well when you've got something that's got mass or inertia. Because as this pendulum comes back to the 0 point, the effect of gravity is reduced until, as you say, if I let it go here, gravity's not doing a damn thing. But because when I get to there, gravity stops doing its thing, but this has got a mass and inertia, it continues swinging. So that's why we get this oscillation. Woo, woo, woo. See that? And if you have the proportional, the P on your flight controller turned up too high, your quadcopter will oscillate too because it's yo-yoing past because it's not anticipating the fact it's going to go back to the correct position, and it overshoots, and you get the oscillation. The higher the gain, the more proportional feedback you have, the worse that oscillation. If it's too bad, it'll just flip because it goes way past the point of no return. So the present proportional measures the present position of your quad, or the present error that needs to be corrected. It only works in the present. So that's the problem, because if you take instantaneous snapshots and your pendulum goes from there to there, at that instant, which is the present at that time, it's fine. So it just turns off the corrective signal, and the inertia then takes your pendulum back past that point. So it doesn't take into account the past or the future. It's a very limited feedback mechanism, just using the proportional. That's why we have these other things. We've got the integral. And that basically looks at things that have happened before. And that's important because one of the problems with our correction method here is that if we have a very slight tilt on our quadcopter, or our FPV glasses in this case, the amount of correction being applied by a proportional feedback is very, very small too. So if it's small enough, you might not get any actual correction occurring at all. What that means is that it can actually just hold a little offset for quite a long time. So it gets all loose around center, because the closer it gets to the right position, the less feedback you're getting from the proportional side of the feedback system. So it means big angle, lots of feedback, little angle, not much feedback. So it gets all wobbly and loose around the center. That's not very good. And if you try and make it tight around the center, you end up with so much gain that it wobbles and crashes. So the integral does something really clever. It looks at what's happened before. It goes back a bit in time because it's keeping a track of where this has been. And if over time it finds that this angle has been sustained, it says, that's not right. We need to correct that. So it then starts producing another corrective feedback force, which will force it to go level. So the integral feedback actually increases over time. So whereas proportional is constant, reliant only on the angle, the integral feedback will over time increase until it's enough force to push your thing back to the right position. So we can't use proportional on its own without getting oscillations. We can't use integral on its own because it's too slow. It would take forever for your quadcopter to right if it got kicked up by a gust of wind. It would be really, really horrible and sloppy. So proportional deals with what's happening right now. Integral looks at the past and takes into account the fact that something has been, hasn't been corrected sufficiently, and it will add the extra correction. Really important. Then we've got derivative, and this is a really freaky one because this is looking into the future. This is time travel shit. What happens with derivative is it doesn't look at the present or the past. It looks towards the future. It tries to work out what's going to happen next. So if your quadcopter is rapidly rotating, it can see, hey, it's rotating, so in X units of time, it's going to be here in the future. So what it can do is then apply correction. Because, for example, if you've got this big angle here and suddenly it's been corrected, and the derivative software works out that if we wait too long, it's going to overshoot there, derivative can apply a correction to stop it at just the right time by anticipating the movement of the quadcopter. So derivative will damp out those, if you do a sudden change of pitch or roll, and don't have enough derivative, it will wobble like that. But if you wind the D up, it will damp it and it will stop exactly because it's anticipating, thinking, this is going to go too far. Our pendulum, for example, is going to swing past the 0 point and we're going to have an oscillation. So what the derivative does is it says, I know the pendulum's going to be here, and when it gets there, I'm going to apply a corrective force. So in that case, with the right PID setup, your pendulum just goes pop and stops. It doesn't rock backwards and forwards. If you had integral, your pendulum would take forever to get back to the right point because it looks over a long period of time and averages all the numbers. So it's a very slow correction. If you had proportional, then you get this oscillation. And if you have proportional, integral, and derivative all mixed together in the right proportions, then the pendulum stops exactly where it's supposed to be. And the same happens with your multi-rotor. When you've got your PIDs tuned, it responds immediately to your stick inputs. And when you stop putting a command, it stops exactly. And it feels locked in and tight and directly connected to the sticks. That's what PID do in simple terms. What I'll be doing in a future video is showing you how to make sense of this in terms of programming your flight controller, what to look for. But what I've tried to do here is simplify this whole PID thing and basically explain how it works in terms of the inputs that are being put back in here, this feedback loop, how each one of these does something different to make for a feedback loop that doesn't oscillate, yet is very quick to respond. So there you go. I'll probably confuse the snot out of you. Never mind, that's what I'm here for. You've got questions, got comments, let me know about this PID stuff, and I'll do my best to elaborate further.